Okay, let's talk about chapter 27, which discusses active galaxies, quasars, and supermassive black holes. So we'll talk about what quasars are, SMBs, and how they're related to quasars, and then using quasars to understand the evolution of the universe. Okay, so what is a quasar? It's short for quasi-stellar radio source, and because the quasi-stellar, the signal when these were first generated looked similar to maybe stars or something, but we weren't quite sure of the origin of them. So quasi-stellar just means very strong emission that was similar to radio waves. So this here is showing a picture that's pointing out a quasar here, PKS 1117248. Note that nothing in this image distinguishes the quasar from an ordinary star. That's the quasi-stellar nature of it. But when you look at it under a spectrum, you see that it has a very high redshift. It's moving away at 67,000 miles per second. Whereas the maximum observed speed for any star in our own galaxy or even in a galaxy is a few hundred miles per second. So this is looks like a normal star, but when you look closely at it, it's got some unique properties, mainly that it's flying away from us. So we started looking at these other objects, and here's a cool one. Blah, blah, blah. Note the faint streak going towards the upper left. So there's this streak coming out of this quasar here. This is pretty cool, and it's an ejected material going at a huge amount of the fraction of the speed of light and 200,000 light years long, so it's a massive jet of material being ejected. So by looking more closely at these things, we started to realize that, these are not quite stars, and potentially they are something completely different. So here's an example of two bright stars in our own galaxy, and one between the two of them, one is a star and the other one is a quasar. That's 9 billion light years away. So the whole point of this is that just by looking at it, it looks like a star. It's quasi-stellar. It's hard to tell just by looking at it. So again, you have to look at the redshift of the galaxy from the Doppler, from its velocity moving away. So the redshift is just calculated as the change in the wavelength divided by the wavelength of the light at rest. So normally the Lyman alpha line of hydrogen might be 121.5 nanometers, but if it's redshifted by a few nanometers to be 119 or 125, some shift in that amount, then you can use that to estimate the velocity of the galaxy that's moving away. So for example, if it's 393 nanometers, which is like what a black light is when you go to party or something, let's say you measure a shift to be 7.86 nanometers away longer than that. So it would be 400 nanometers, so it would be redshifted. Then you just, the change in wavelength is 7.86, so 7.86 divided by 393 nanometers tells you that it's 2% shifted from its regular spectrum. So that means it's traveling at 2% the speed of light. So that's the quick way to measure the distance to something. And so they just go through here to do some calculations. So it turns out that quasars also obey the Hubble law, which we talked about in the last section, which tells us that the universe is also expanding according to quasars. So what is a quasar? Anyway, this is talking about the energy of a quasar. Look at this. This massive jet of particles shooting out of the quasar or something at the center of this galaxy. It's not a quasar, but this huge signal, and it's in X-rays and radio, it's in visible light, whatever's coming out of there, it's tons of stuff. This is called active galactic nuclei. Okay, and an active galactic nuclei means that the center of the galaxy, this is a large elliptical galaxy, the center of it is active, which means the black hole at the center of the galaxy is accreting matter. So it has an accretion disk and it's accelerating the particles in the strong magnetic fields, will eject particles at very high speeds. And we can see that here. Okay, so what is a quasar then? What's going on? A quasar is simply a active galactic nuclei, a black hole emitting a huge amount of energy, basically. Um, so blah blah blah. Let's continue on. Find it better. Yeah. So this idea that at the centers of these galaxies, yeah, look at this red shift and blue shift here. M87 is the um, uh, galaxy that the Event Horizon Telescope took a picture of the black hole at the center of it. And so we have the event horizon now of that thing. This is yeah, another galaxy with a black hole disk here. Okay, so energy production. So yeah, I mean, you get friction and everything when things are rotating at that speed and bumping into each other. These are this Fermi bubble, this large bubble of energy generated by the black hole emissions, so Fermi bubbles. Those are pretty cool. Radio jets come out of these things. So you have the disk of material around the black hole, just like Saturn has rings. The black hole would have an accretion disk of matter, and then you have jets of particles spraying out in either direction. And so depending on the size and shape of the accretion disk, that changes the size and shape of the jet that comes out. And that jet, if it's pointed at us, will show up as a quasar. So here's another cool picture of a jet coming out of the center of this galaxy that's really far away, and the supermassive black hole at the center with the accretion disk, which is pretty awesome. Okay, so quasars, yeah, this is the number of quasars and the time since the Big Bang. And so you can see that there's um, correlation between the quasar formation and star formation in the history of the universe. Oops. So that tells us, helps us understand the history of the universe, basically. And if you look at the size of the central black hole and compare it to the mass of the central bulge, there's a correlation there. So uh, every galaxy has a black hole at the center of it, and depending on the size of the galaxy, it seems to correlate with the size of the black hole. So that's pretty cool. So here's some data here that's trying to find that correlation. Okay, blah, 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 more stuff here. This is an example of a star that turned into or fell into the black hole and gets sort of eaten as it falls in, which is kind of amazing. So during that process, right, it would glow very brightly. There might be a flash of light that we could see from Earth, and the mass of the black hole would increase a little. Here's two galaxies that are merging. Each has a black hole, so they would eventually merge. Let's see, how does the black hole influence formation of stars and galaxies? The answer is not much. We actually don't know what came first, the chicken or the egg. I mean, in real life, right, the chicken came first and then the egg came second. But for supermassive black holes, did they form first and then the galaxy formed? Did they sort of form at the same time? Or did the stars form first and then the galaxy or the black hole form? So that's actually a question of what is the cause of this thing. So open question. We're still working on that to try to figure out exactly how you could get a supermassive black hole. And there's a bunch of different ways, so we got to narrow it down based on the evidence that we see out there. Okay, so in summary, quasars are quasi-stellar radio sources. They are active galactic nuclei, which means they're a black hole with an accretion disk. And anyway, let's continue on. Yep, so both active galactic nuclei and quasars derive their energy from material falling inward and forming a hot accretion disk around a black hole. So some quasars could be the supermassive black hole at the center of the galaxy or a different one. And quasars probe the evolution of the universe because they also follow the Hubble law, and then we can also measure the number of them as a function of time to help us understand what's going on through history. Okay, and that's it.